And welcome, and we're so happy to have you and to kick off our 2021 OSU Medicine 411. It's something that we put in place last year whenever we weren't able to host Operation Orange, and this was just a way to still reach you all virtually. So whether you're here in the local Tulsa area or across the country, we're so glad that you're here with us this morning. If you need proof of attendance for whatever reason, if you'll just shoot me a message, I will make sure to get that over to you after the program today. And we are going to be recording. We have some people that weren't able to make it live, so just a heads up. And just want to thank our sponsors. We have them all over the state, and we really wouldn't be able to put on these summer programs without their help. So a big thank you to them. So today for OSU Medicine 411, we'll have 3 sessions. The Zoom link you're on is going to be good for all 3 of those, so you can stay on or you can join those again later. Today we'll kick off the event with anatomy, which is going to be led by Dr. Daniel Barter and Eric Snively. After that, at 11, we'll hear from one of our current biomedical science students on his experiences, and then again at 1:30 from a forensic sciences student. So Dr. Barta and Eric have said that they would love to hear from you all, so be thinking of questions as we go, and there will be an opportunity for you to ask them at the end of the session. So as for now, here are your hosts.
All right, Dr. Snively, I'll let you go first.
Thanks, Dr. Barta. So I think I will share my screen here, and I'll hit share, and I'll just give you a quick introduction to us and what we do. So hopefully this will work. I'm not sure if, hopefully you guys will be able to see the, can you guys, yes, there we go. So we are professors at the Oklahoma College of Osteopathic Medicine at the Cherokee Nation, and we're the first tribally affiliated medical school in the country, and we're very proud of that. So here we have where we work. This is the College of Osteopathic Medicine, our Tahlequah branch on the Cherokee Nation. And Dr. Barta and I teach anatomy. So we teach the anatomy of the entire body. And then we also teach a little bit of neuroanatomy, which is the anatomy of the brain and the nervous system and neurons and things that help us do what we do. So I'm going to talk about a little bit about the anatomy of the body below the head. And in other words, we're going to actually look at the anatomy of the leg. And Dr. Barta is going to have some really cool stuff about the brain. We have some videos and some interesting props to show you. We'll tie this all together. And Dr. Barta and I are paleontologists. And you might ask, why would people who study dinosaurs teach at a medical college? And the reason is that anatomy is very linked across animals with backbones. We'll actually show you some really cool examples of that. But first of all, we can get started with anatomy of humans and some of the tools we use for diagnosing both human anatomy and sometimes even for examining dinosaur anatomy. So you guys may be familiar with CT scanners. They're often called CAT scanners. And that means computed tomography or computed axial tomography, where we kind of slice up the body, but through X-rays. We put those back together as representations of the entire body. So here we see a medical practitioner and a gentleman who is being scanned here, and she's ensuring his safety and ensuring that we get the maximum resolution for whatever ailment he might have. So we can, again, look inside the human body by putting it through a CT scanner. What I'm going to do is show you some videos of CT scans of the human lower limb. So if you guys can see this, we'll have a video of kind of stepping through part of a human body. There's a bunch of other things on the screen, but just focus on what's central there. And there we can see some feet appearing. We can see the 2 lower leg bones kind of receding there. We're stepping through the entire body. There's the knee that Dr. Barta is a real expert at. And we're now up into the upper leg. And you can see here the muscles surrounding the upper leg bone. There's our upper leg bone. We can see some fat surrounding the leg bone as well. And that's great. So we can go to any point along here and we can see this individual has maybe some pretty sparse and fluffy bone in her knees. She may have osteoporosis. So that's a thing that causes people to often break their bones because the bones are very fragile. But we can do other interesting things with this. Here is a three-dimensional representation of the legs of the same person. And we're going to show what we can do. See it sort of swinging up towards us there. And we can see these cross sections in 3 dimensions. Not only that, we can color code how dense the bone is. So for green here, she has pretty dense, strong bone. Where it gets to be purple, it's pretty fluffy. And we can tell where she may have some issues with her bone breaking. And also this is kind of cool stuff about anatomy, where we get all of this fluffy, spongy bone, we tend to get that at our knees. And that's really great for handling forces as we're running and walking around. We tend to get this bone that's almost a lattice work of struts in our knees and in our hips, where we need to spread those complicated forces out a lot. So what you're seeing right here is something that one of your physicians can do, that Dr. Barta and I can do if we're interested in human anatomy, when we can examine the density and the internal anatomy of our bones. So that's all pretty neat. And here at OSU, the Comms CHS here on Cherokee Nation, we have a 3D printer. So we can actually take some of those CT scans and we can put the data into a printer. Here we're seeing a lower leg bone, a tibia, taking shape. Here's the medullary cavity. This is where the bone marrow is. Here the printer is making a lattice work of the bone so it can print a good light solid. And here's our student doctor, David, who is David Ray, who is removing the bone now from the printer. David actually produced this bone model from a CT scan, and now he is printing it. And I can actually show you guys, stop the share here, show you guys the model that David produced. And here it is. So this is a model of the tibia, the lower leg bone, of the same woman whose CT scan we saw. This is a little bit smaller than life-sized, but the printer it's actually so good that it kind of shows the errors that I incorporated into student Dr. Ray's model when I was cleaning up this tibia here. So here's again, tibia, which is a lower leg bone, the big lower leg bone of a human being. And Dr. Barta and I are both, of course, paleontologists. We're interested in the anatomy of other animals. And one of the things I do with CT scanning is I do CT scanning on what's called a synchrotron, which is essentially an atom smashing machine. And we're able to get really, really powerful X-rays from this system. So what I'm going to do now is show you the interior of a bone in 3D, but then we're going to have Dr. Barta show you what the bone looks like in a dinosaur that he studies. So I'm going to share the screen here. And I'll hit share, I have to do that. And here we have some blood vessels within the bone of a dinosaur. It's spinning around there, and we can tell the thicknesses of those blood vessels. So that's pretty cool. It looks really fancy, but we don't really understand quite well what this is really telling us. So Dr. Barta is able to see much finer detail with the physical methods that he uses to study the tissue structure of animals, including dinosaurs and humans and ancient relatives of mammals, including humans like us. So with that, I believe I will turn it over to Dr. Barta, and he'll show you some of the cool work that he does, and we'll continue on from there.
Okay, well, thank you, Dr. Snively. So, like Dr. Snively said, there is this real connection between, the anatomy of all animals with backbones, including those that are now living and those that are extinct, like this dinosaur we're looking at. Can everyone see this okay here? We're looking at the dinosaur eye study called Cephophysis. So this is a small carnivorous dinosaur, very, very early relative of things like Tyrannosaurus rex and Velociraptor that you might be familiar with. And so I'm really interested in looking at bone histology, how bone grows and develops. And this is a good dinosaur for studying this in because we have a lot of different individuals. They were all sort of preserved together, buried together as a population. And so I actually physically cut through on a specialized type of saw the fossil bone of the tibia of this animal here. So a section about at the mid shaft of the tibia is what we're looking at. And so I think you can see that here, fairly large. And so this is actually a really interesting bone thin section for many reasons. I'll talk about just a couple of them. So we can zoom way in. This is a very high resolution photograph that I took on a specialized microscope. And so if you see all these black squiggly lines here, those are the blood vessel spaces, the spaces where blood vessels used to be, that Dr. Snively showed you his synchrotron reconstruction of what those vessels would have looked like in 3 dimensions. This is essentially just a 2-dimensional slice. If you think of like slicing up a sausage, we're looking at like one of those little kind of round pieces that you take out of the middle, and we're looking at it transversely. So you can see the spaces where the blood vessels used to be. This is a 200 million year old dinosaur, so really incredible that we can still see that. And even more remarkable are all these little black speckled dots here. These are the spaces where the bone cells used to be. So we call these cells osteocytes, and they're the cells that build and maintain the bone. And so I think it's really easy to sort of fall into this trap of thinking of our bones as just a static, unchanging tissue, that like our bones are always the same way that they were when we were born. And of course, we know that's not the case, right? Your bones have to grow because we have to go from the size of a newborn to the size we all are now. And so your bones are always growing and changing throughout your life, even after you reach adulthood and your bones sort of stop growing in length. Your bones still respond to stresses that the environment places on them. And so I think this bone is actually kind of an interesting scientific mystery that my colleagues and I are currently looking at, because we think it might show some evidence of bone responding to stress. And so if we look around the edge of the bone, it looks fairly uniform. We see some color differences, but largely we see the same type of blood vessel spaces all the way around until we get to this point. You probably notice this this region right here that I've highlighted with the dashed line. And this is a type of bone that grows super rapidly. We can see all of these blood vessel spaces in here are they look like they're vertically up and down on the screen. They really would have been growing radially outwards from the center of the bone out towards the exterior here. And this is a type of bone that is laid down really rapidly, oftentimes when bone is subjected to extra stress beyond what it would normally experience. And so one of the things we're trying to figure out is, why does this bone have this one little patch of this really rapidly growing bone? And in some other dinosaurs that our colleague Dr. Ballard here at Oklahoma State has studied, she found a dinosaur in which one of the legs, I can't remember if it was the left or right, but the leg on one side was broken, and the dinosaur therefore had to put much more of its weight on the other leg to compensate. And so I suspect something similar might have been going on here, that the other leg of this coelophysis was injured. And so this leg was kind of taking up the slack and had a lot more stress on it. Therefore, that bone had to grow much thicker very rapidly to compensate for that injury. But that's just a hypothesis. We're looking at different types of bone tissues that form under different conditions to try and test that hypothesis. Okay, so now to sort of totally switch gears from the leg of a dinosaur to the brain of humans. Our second year medical students here take a course called neuroanatomy. So our first year students, they learn about the anatomy of essentially the rest of the body. And then the second years get to learn about the brain. And so I have a model of the human brain here. This is actual size. And so in the real course, our second year med students dissect real human brains from our donor bodies. So the bodies we have here are people who have very graciously donated their bodies for use in teaching and in some cases research. And so this is a model here. And so this gives examples of some of the types of dissections that our second year med students get to do. So if we look, this model has been sliced in half. So we can actually look at sort of the interior of the brain here. And so I'll show you on a screen some of the features we're most interested in. I want to the brain is a very complex organ. There's a million things we could talk about in relation to the brain. But I want to talk about one part in particular that's related to memory. So we've seen the brain sort of sliced in half here. And Dr. Snively knows a lot about various other parts of the brain that he also lectures on. But we're going to take a look. We're going to make a sort of a simulated slice just like this. And we're going to remove sort of the midbrain. And we're going to look down into what we call the temporal lobe. So the temporal lobe is the portion that actually is sort of alongside your temporal region in your skull. And so when we look down inside, we're seeing this portion that we call the hippocampus. And it's surrounded by this plexus of veins. So it's a little bit difficult to see here in the model, but it's this curved structure right along here. And so I'm going to switch to a PowerPoint to illustrate this a little more clearly here. Let's see here. Sharing that again. There we go. Okay, and so here we have the hippocampus. Again, I said it's kind of that curved part. Again, it's in the temporal lobe of the brain. So this portion that sort of curves forward in your temporal region. And so the hippocampus, it looks like this. It's so named. Hippocampus means seahorse in Greek. It looks like kind of a small little seahorse in there. And so this is the part of the brain that helps integrate sensory information and store it in short-term memory. It's vital for forming spatial memories as well. So if you think about having kind of a mental map of say your school and where all the different rooms are and things, that's your hippocampus takes the information that you take in with your eyes. So when you're navigating school for the first time, like if you think back to your first day of school, that's all the sights and sounds and senses. Those are being taken in by your eyes, your nose, your ears, all the senses we're familiar with. But then how that information gets stored as memory information. All of that is happening in the hippocampus. And so just to show you kind of a drawing here of what some of this looks like. So there's the hippocampus again in green. We can see that temporal lobe kind of sweeping forward here. This is the middle of the brain. So there's a lot of names on here. These are sort of the specialized things that our second year med students learn. But essentially, sensory information comes in through our cranial nerves. So the cranial nerves are nerves that they do a lot of things. Some of them are involved with our senses. So right here, this is the olfactory nerve. And I can show you that on our brain model again here. So again, we're looking at the brain. This is the front of the brain. This is the back of the brain. So if we flip up the brain, we can see right here, this little white stripe here. This is the olfactory nerve. And so it gives off lots of little branches that actually go through down into sort of the soft tissues in your nose, brings smell information back to the brain. And so say, for example, you're over at your grandma's house and she's made cookies, and that sensory information is reaching you. That travels back along the cranial nerve. And then there's also a structure in here called the amygdala. And the amygdala is linked to the hippocampus as part of this greater thing we call the limbic system. And the amygdala is what kind of gives emotional context to memories. So if you think about kind of how you feel, say you're at your grandma's house and you just made cookies, like sort of those feelings of, hopefully warmth and sort of safety and family togetherness, that scent becomes associated with those emotions. And those two things are integrated together in the hippocampus to form that memory. And then eventually it gets stored in your long-term memory as well. And how exactly that happens is something that's of great interest to neuroscientists. It's really kind of one of the more mysterious parts of the brain is exactly how all of these memory circuits work. And it's also of great interest, of course, for things like Alzheimer's disease. We know that there can be degradation to the hippocampus with that disease. And so a lot of research by neuroscientists is targeting that area to understand things like the progression of Alzheimer's. So that's just an example of how we can go from the anatomy that we can see physically in the brain and dissect, and how we make those connections out to larger sort of clinical diagnoses and areas where scientists are actively researching disease. So with that, I want to make sure we have time for you all to ask questions of us. So I will let Ashley maybe handle the questions as they come in. We would love to hear from you, and we just really want to thank you for being a great audience today.
And if you have any questions for us afterwards, please feel free to email Ashley, and we will do our best to answer those to you personally.
Yes, well, thank you both so much. That was so interesting to hear about all of the details and kind of what makes up our skeletons. So like they mentioned, if you guys have any questions, feel free to just unmute and ask those, or if you want to send them over in a chat, we'll give you guys a couple of minutes to do that.
As we're waiting on questions, I believe Dr. Snively had one more thing to show us, possibly. So
yeah, sure.
You can switch over to questions as they come in, but I think you had one kind of cool dinosaur-related thing to show us.
Well, it relates to cranial nerves, like Dr. Barter was talking about. So humans and dinosaurs have all the same bones, and we often have the same sort of structures in the bones that tell us where cranial nerves and blood vessels are going, like the olfactory nerve that Dr. Barta mentioned. There's another one, if you give me a second here, pretty neat nerve. So again, as you're formulating questions, feel free. So I can't see myself very well here, so hopefully you guys can see a dinosaur. And there's a certain cranial nerve that relates to a little disease malady that I had, where I had tingling and weird pain sensations through my eye socket and on my head. And that's a nerve called the frontal branch of the ophthalmic nerve. And this is a dinosaur, kind of tyrannosaur. And this nerve would have traveled right up through here onto the forehead of this tyrannosaur. So that's the kind of connection that we can make clinically, even to an angry, sad dinosaur with a certain disease that I had as well. So another cool look at this. This is a tyrannosaur called Alliaramus. And we'll see if we have any questions. If we don't, that's great. What is the nerve called? Thank you, Ashton. This nerve is called the frontal branch of the ophthalmic branch of the trigeminal nerve. So it's actually also this, you can call it the supraorbital or above the eye socket. Supraorbital is good, call it that, S-U-P-R-A-O-R-B-I-T-A-L. So I had an issue with that nerve, and maybe this dinosaur did too.
So is it called the supraorbital?
Supraorbital, that's a good way to put it, yes. Thanks, Ashton.
And it's above the eye socket.
It goes from through the eye socket out onto your forehead.
So I'm just kind of taking notes right now.
Excellent. Anyone else? Alyssa or Rayleigh or Reva or Karan, anyone else with a question, we're happy to answer.
Do you have any questions about the medical school in general too? It doesn't have to be about anatomy. We can kind of speak to maybe a lot of things, hopefully, about, you know, if you're interested in either going to medical school someday, or if you want to do scientific research. I think, you know, we can answer questions about that, you know, sort of from our perspective, at least, as paleontologists.
Hi, can you hear me?
Yes. Yeah.
Caitlin, go for it.
So what kind of like interested you in like just everything in general?
Yeah. So I guess I'll start with that. Yeah, what got me interested in sort of science and medicine. Yeah, so you know, growing up, I'm from Montana originally, and so Montana has a lot of dinosaur bones, and so there's been kind of this long history of paleontology there. There's a great museum there that I often went to when I was growing up. Much like Oklahoma has the Sam Noble Museum over at that other university, so, you know, I grew up going there, became fascinated with dinosaurs because they're, you know, sort of size and kind of just how they're a bit unlike anything around today, but they also have some kind of cool similarities to things like crocodiles and birds that I found really fascinating. And so really it was dinosaurs got me into it. But then later on when I was in graduate school, I took my first human anatomy course, and being able to just see kind of the wonders of the human body and this beautiful interplay between structure and function, I just found really fascinating that you can think about all the functions our body does to support life, and then you can actually go and see that structure and think about how it functions, and just think about how there are still a lot of things left to discover in terms of preventing disease and things like that. And just the ability to work with our wonderful student doctors, our medical students in training here, they really a joy to work with, and just the knowledge that they're going to go on and you know, help people and do great things, particularly for rural Oklahoma. I think that's a really gratifying thing for both of us. Dr. Snively?
Well, I think I have to be cognizant of time. So
Yeah,
how much time do we have, Ashley?
You guys are great. We don't have another session till 11, so no rush.
Okay,
Oh,
well,
okay.
we can keep going. That's fantastic.
The whole time, but yeah.
Yeah, so like Dr. Barter, I became interested in dinosaurs when I was really small. I was actually my dad was stationed in Utah, and I was getting a haircut in a barber shop, and there was a fossilized dinosaur footprint on the floor of the barber shop. And so I asked my parents to get me books about dinosaurs, and sort of still doing that. And I was interested in T-Rex, and T-Rex is a pretty spectacular animal. And I was interested in how T-Rex bit into its prey. And I was thinking as a tiny little kid, like, how do you move? What do you do to move? You use muscles. So I went to a human anatomy atlas called Gray's Anatomy. I was looking at the jaw muscles of humans. I didn't really understand the words very well, but I could at least state them and had some idea what connections between humans and dinosaurs back then. And I taught at an undergraduate university for a while, teaching anatomy to pre-veterinary students. So comparative anatomy of animals, especially things like fishes like sharks and mammals like cats and reptiles like alligators, taught them about birds a lot. So I had a very broad base. I taught the same class that Dr. Barta had taken, a very similar class. I wanted to learn one animal really well. And so I sort of took on the challenge of becoming a medical school professor, because we learn human anatomy in so much detail that we can impart that to our student doctors, have them go out and serve underserved communities in Oklahoma, for example, on the Cherokee Nation and other Native American nations, and also just generally underserved rural Oklahoma. I thought that was a really great part of our mission. Also other underserved communities. So it's a bit of a challenge because I hadn't dissected a human body in about 9 or 10 years before I came here. It was all overwhelming and new, just like it is to our medical students. By learning, again, one animal and learning humans really well, we can apply what we learn about people to the animals that we study. So learn about the senses of humans, learn about the emotions and memory that humans have. We're similar in a lot of ways in structure, including brain structure and so on, to other animals. And so we can apply what we learn about humans to dinosaurs and other prehistoric or other ancient extinct animals.
So, okay, so you guys are professors, right?
Yeah.
And so you guys focus on anatomy of humans, and then, do you kind of correlate that with dinosaurs, or is it the other way around?
Yeah, Dr. Barta, what direction do you tend to go in?
Yeah, so for me, it's our teaching centers around human anatomy primarily. We sometimes we'll teach some other classes on animal anatomy and stuff, but yeah, I think for me, it sort of depends, I guess, which region of the body I think I'm working on. Like, there's a lot of things that, particularly if I'm thinking about bones, I'm probably saw those structures first in a dinosaur. Like when I'm thinking about bone histology, I sort of have that image in my mind of what the dinosaur bone histology that I've been studying for several years now kind of looks like. And then when I look at, say, human bone histology, I'm kind of bringing that knowledge to it. If I'm thinking about nerves or the brain, I sort of first started studying that in humans for the classes we teach here. And that's kind of given me new perspective. When I see a dinosaur brain case, I see all these holes in it and I think, oh, that's where the ophthalmic nerve would have come out, or that's where the olfactory nerve would have come out. And so I think it really depends. Generally for me, if I'm thinking about bones, I'm probably taking what I learned in dinosaurs and applying it to humans. If I'm thinking about more soft tissue structures like muscles or nerves, blood vessels, I'm probably going the other way, starting with the human anatomy and applying it to my research that way.
It's about the same for me. It depends on what system I'm looking at. So for senses, I tend to look at humans first because we have a fairly good understanding of how we smell and how we see. the whole visual system when we're seeing things is really, really super awesome. And we have student doctors who are actually creating computer models of the visual system for us, how we see with our brains. It's really, really amazing. And I like to think of it comparatively. So if we're looking at this dinosaur here, so there's a Tyrannosaur, Alioramus, you can actually see where the eye was, because a lot of animals have little bones in their eyes. It's called a sclerotic ring. So we can get an idea of the size of the eyeball. And it turns out the bigger eye you have, the better your vision. You just have more spots within your eyeball for sensing light. So if you look at the size of the eyeball comparatively, you can imagine what it's like to be an Alioramus and to look at things. You might have sharper vision than we do as humans. Another neat thing, like we can see combinations of 3 different colors because we have 3 different kinds of cells in our eyes that pick up those 3 different colors. Reptiles, including birds and other dinosaurs, have 4 different kinds of light color gathering cells in their eyes. And they have cool little structures, these little oil droplets over these cells that make their vision even better. So if you imagine a Tyrannosaurus Rex with an eyeball the size of your fist, they can see colors that you cannot imagine and can see probably sharper than an eagle can. So by understanding human eye anatomy, it sheds light on extinct dinosaurs and other extinct animals, and it gives us perspective on other aspects of their biology. Now, I like Dr. Barter, I kind of go in the other direction with bones. I tend to look at like Triceratops, the big 3-horned dinosaur. One of the bones that forms its big frill in the back of its head actually forms the back of our cheekbone. That's just wild. So I look at the frill of a Triceratops and I think, wow, I have that bone. It's like right here. Like, what the heck? That's amazing. So for bones, like Dr. Barter, I think of dinosaurs first.
If you all want to see the optic nerve, so Dr. Snively was talking about how you're bringing in all that sort of light information, that sensory information from your eyeball, and it has to travel back to your brain. And so on this brain, we just have a little stump of it left. This is what it looks like once we dissect it out of the skull. But this little nubbin right here, this is sort of right where the optic nerve, which actually goes out towards your eyeball, this is where it comes back to the brain. And then that information is sort of integrated in our sort of sensory processing centers in the brain. So again, there's a structure for every function that you can think of, and that's, sometimes you think about, you hear like, it's brain surgery or something is like rocket science, the synonym for something like super complicated. And don't get me wrong, it is complicated. Our medical students have a lot that they have to learn and a lot of information to take in. But the brain isn't some sort of like magical black box where like inputs come in and outputs go out and like we don't know anything about what happens in the middle. Like there are structures and pathways and different fiber tracks that carry information input in the brain, and we can trace out where those all go. We can trace how they come in from the senses and then sort of the outflow from the brain to the spinal cord to nerves that are giving your muscles the signals to move when they're under voluntary control. So there's a lot of frontiers in neuroscience in terms of things that we still have a lot to learn about, and that imaging techniques like MRI are helping us learn about. But there is like a concrete reality to all these things. There are structures that we can look at, which is, good news for trying to diagnose disease. A lot of times we can use symptoms to help guide where to look on the brain to figure out, say there's a particular surgery that needs to be done. The symptoms will oftentimes guide doctors to where they need to, say, do surgery on an aneurysm or a tumor or something. So there is the structure and function. I keep coming back to that. That's kind of the at the heart of what we do, whether it's on extinct animals, whether it's on living animals or humans.
A question from Karan. Have you guys excavated any bones? And if so, how many? Dr. Barter, do you want to start with that?
Oh my goodness, yes. So I have excavated dinosaur bones and bones of other extinct animals that lived alongside dinosaurs, things like small mammals, lizards. How many? That's a great question. I haven't necessarily thought about counting them. In a really good field season, I'd say it would probably be dozens. In a good field season, I've had days where you just don't find anything. You just wander around, stare at the ground, and all you see are rocks. But there's certain areas that we do field work in that are super productive. So Dr. Snively can tell you a little bit about what it's like to do field work in Western Canada. There's amazing fossil fields out there. I've done field work in Mongolia and China, as well as Montana. And those places are really productive as well. We find a lot of dinosaur eggshell. We find occasionally whole skulls or skeletons of things. Sometimes I've found teeth of things like a dinosaur related to Velociraptor. I've found the jawbone of a Protoceratops, a small, little early relative of Triceratops. And probably some of the cooler things I've found are these little lizard skulls in the Mongolia's Gobi Desert that are essentially complete down to basically every last bone. And then those can be put in a CAT scanner and scientists can look inside those skulls. So, those are some of my favorite things. Those are some of the most memorable. I would say some of the egg clutches and some of the lizard skulls are probably some of the most memorable. I did help out digging up a Triceratops skull once as well. So per season, if it's good season, I would say probably dozens of bones. But Dr. Snively can speak to his fieldwork experiences as well. I really like digging up smaller dinosaurs because they don't take nearly as much work to get out of the ground. We for large bones especially, once you find the bone, weathering out the surface of the ground, you have to dig essentially kind of a trench around it, and then you wrap the top of the bone in some sort of separator layer. Usually that is, sometimes we use like paper. Other times we use sort of the separator layer, and then we put burlap soaked in plaster over the top. So that same kind of plaster that you use if you have a broken arm to help the arm heal and prevent the bone from being broken further. We use that same kind of plaster jacket to cover over the bone and the rock together. And then we transport that jacket back to the laboratory. Then we open up the jacket, and we have technicians called preparators who remove all of the excess rock from around the bone. And then that leaves you with something that looks, like the bone did when it was inside the living dinosaur at one point. And then it's ready for the further kind of analyses that we talked about. So Dr. Snively, you want to talk a little bit about your fieldwork experiences?
Sure, yeah. So
favorite bone was?
Yeah, so we have, Srikar asked per season. That means that we're typically out during the summers.
Mm-hmm.
And that's when we're excavating bones. And our field season can last however the weather allows. So it can be 3 months, 6 months. Dr. Barter and I have only been out I've been out a maximum of 3 months at a time. So we're not necessarily out there as much as some other paleontologists. I excavated a lot of bones in Western Canada. So I was in Canada for 12 years. The most memorable individual bone I excavated was, it was part of the back hip bone of a T-Rex that I found. I saw eroding out of a hillside, and immediately I knew what it was. It's from what we call the apron of the ischium, which is like a flat part of this back hip bone. So that was pretty neat. In the same same environment, I helped excavate an early version of Triceratops called Eotriceratops. And it had a frill, the skull overall, that was a bit longer than that in Triceratops. And that was fun because it was basically down a cliff. And it was down a cliff at the bottom of another steep hill. So we did not have cables for winching the field jackets that Dr. Barter talked about. We had these big field jackets. We had to drag up these cliff faces, basically. So we actually winched another truck down to the lower level, so its cables could reach these field jackets of this Eotriceratops. So I got to work the winch and made sure that the field jackets and the trucks made it back up the hill. So that was pretty fun. Yeah, a lot of really cool stuff. Several duck-billed dinosaurs that I've excavated, both juveniles and adults. I was in charge of a quarry where we excavate bones of horned dinosaur. It's a Centrosaurus, so it had one big horn on its snout. And I did a lot of collections of individual bones because we're interested in the ecology of the area. So where Dr. Barter works, you get an awesome feel for the small animals that are out there. And where I worked, we didn't find bones of a lot of small animals, but we realized we can do a census of dinosaurs if we go out and collect individual bones. So instead of getting a whole skeleton of a dinosaur, we collected the bones that normally we wouldn't excavate because we already have too many. So that was really exciting and rewarding, sort of contributing to our understanding of dinosaurs in a certain part of Canada. It was about 10 million years before the end of the age of dinosaurs. So what other questions might you guys have?
Okay, well, if there's no more questions, like they mentioned, if you think of anything later on, feel free to send those over to me and I will make sure to pass those on to Dr. Barta and Dr. Snively. But thank you again. That was so much great information. We really appreciate hearing from you guys and hearing the paleontology aspect. That's been just extremely interesting. So thank you guys again.
Yeah,
Great to
thank
see
you
you
all. Yeah,
Great
thanks for being a
questions.
great audience and enjoy the rest of your sessions today.
Started. Welcome again, and we're so glad to have you, whether you're from local or from around the state. That is one of the great things about being virtual. You can always tune in. So today we're going to have our second session hosted by Dalton Delaney, who is a current biomedical sciences student and a current medical student. So he's actually taking on both degrees. Like the Zoom just announced, we are going to be recording this session. So if anyone wasn't able to attend live, we'll be able to send that out. Or if you want to watch this back later, I will send that out at the end of the week. We encourage you to ask questions. So if you think of anything, we'll give you an opportunity at the end of the session, or you can chat it to me and we'll make sure we get that answered for you. But for now, I will hand it off to Dalton.
All right, thank you, Ashley. So like she said, my name is Dalton Delaney. I'm a current DO PhD student. And so what that means is that not only am I working on research and working in the biomedical science field, but I'm also working in the clinic. And actually, I'm taking a break from clinic work right now to speak with you all. And so I'm from Oklahoma. I was born in Ponca City, Oklahoma, but graduated from Blackwell, Oklahoma. So there's, small town. There's roughly 7,000 students. I graduated with roughly, I want to say around 100 students in my high school class. So not very many. And let's see what else. So again, I graduated high school, went on to Northwestern Oklahoma State University in Alva, Oklahoma. And while I was there, I played football for my freshman year. And during that time, I was also taking all my courses and was learning a lot about sciences, learning a lot about chemistry, learning a lot about biology. And what I tried to do was try to use those things to be able to do research on how to make myself a better athlete. Always trying to read the most current up-to-date research, always trying to figure out what I could do to give myself an edge playing sports. And while all of that was great, I was spending a little too much time doing my outside studies and not as much doing my actual studies. So after about 2 years at Northwestern, I had suffered an injury to my right shoulder, and that kind of put me down for a little bit and had me reevaluate some things in my life to figure out what was important to me. And so when I was making that transition, I thought to myself, well, sports are amazing. I love sports. I've been an athlete my entire life. But I also really found this research fascinating. I love to be able to learn more so that I could do more with less. Again, I come from rural Oklahoma, a single parent family. We grew up with, limited resources. And so it was really important for me to be able to learn how to do more with less. And so when I was trying to figure out where to go next and what to do next, I was looking around at other universities to see their degree programs that they had. And during that time, I found the University of Central Oklahoma in Edmond, and they have a kinesiology and exercise science program. And I thought, well, that's perfect. That is what I want to learn. I want to be able to learn more about health and using that science to be able to not only help myself, but to help others. And so I ended up moving across the state to this new university. And there, once I got into that program, everything kind of changed for me, academically speaking. I found I was in the right spot, I was in the right environment, and from there, my academics started skyrocketing. And so during that program, like I said, they taught us a lot about health. They taught us a lot about exercise. They also still touched on the biology, the chemistry, the physiology, all, and showed us not only how to train athletes, but also how to help other people, like senior adults. Exercise is medicine. It's one of the most important tools we have. Not everything has to be drugs. Not everything has to be, surgeries or anything like that. Sometimes we just need to move more. We need to eat better. We need to do things to take care of our bodies so that we don't have to spend so much time trying to fix them after they've been broken. And so while I was there, I was exposed to a research group that they worked with senior adults. And so we would spend time over at retirement homes working with these senior adults, having them lift weights and having them do fast movements and doing all these things that, I was doing in for football practice. And it just kind of amazed me. I didn't realize, why would I have grandma do this? Well, guess what? Grandma did that, and they improved. That was the important sticking point for me, is that it improved their life. And so we took that research and we went to San Francisco to present that research. I'll tell you, the school paid for it. They made sure to take care of everything. They flew me out to San Francisco. There's a lot of opportunities in college to get to just go and travel and do all these fun things. We traveled, and during that conference, I was privy to listening to a celebrity physician, or one that works for a news site, one of the chief medical correspondents. And, while I was there, I was wondering, why is there a doctor here and not just a bunch of personal trainers? Well, it was there that I really found out exercise is medicine, like I had said previously. And so that was really the first step into where I thought to myself, I could go and be a doctor, whether that meant I could go and do this research full time, or I could go and see patients and help them with that. And of course, now today I'm working on both sides of that spectrum, working to be able to do the research in the laboratory, and then taking it into the clinic and being able to see these patients utilizing some of that research. So it's really a two-way street, that they both kind of benefit off each other, because then sometimes I'll be in the clinic and I'll see patients and I'll think, that was an interesting patient. They had some interesting things going on. Is that something we should look up and look into the research to see if there's anything that's been done for that? And so sometimes there is, and then I can go back and help those patients, or maybe there's not enough research done, and then I can go and conduct the research myself, or collaborate with someone else to be able to do that. So now I'm in the final 2 years of my 7-year program, and I know that sounds to many of you guys, 7 years seems like just so long. I'll tell you, the journey has been the most fulfilling part of my life. Getting to be able to learn, getting to work with these people, getting to work with my peers in medical school and in graduate school. The journey has been worth it. And I'm fully submerged in all of these experiences, and I'm so grateful to have them. So afterwards, after I get done with this, I plan on joining a residency. So most physicians or student physicians that get done, they go on to do a residency where in their specific specialty. And with that, so since I have a graduate degree, a PhD, I want to go and work at an academic affiliated hospital, just like OSU. So the best part about this place is not only do we have access to laboratories to do research, but I have a teaching hospital that's right across the river from where my apartment is. And so I really get the best of all worlds, working at an academic, university affiliated hospital. And so I plan to continue my research and continue my clinical training after these next 2 years. And so some of the questions that we have here are, if you guys are interested in any of this, what are some things that you could do to get more exposure to graduate school or to medical school, or even the different degrees to be able to get to here? And I'll tell you, there's no one ultimate path to do anything. There's so many different ways to get to where I am, and I think that I like to think that I'm a good example of. There's what's the saying? There's more than one way to skin a cat. I don't know if I appreciate that saying all that much, but there's multiple ways that you can get to where I'm at. And again, just finding that by reaching out to these programs, reaching out to the recruiters, asking questions, trying to get that exposure, doing some reading on your own. What can I do with this degree? What are the opportunities that, even the institution, like I said, my institution was able to pay for me to go and do research, and took me across the US to be able to do it. And I've had that same privilege here at OSU CHS. They took me to San Diego, a few years back before COVID. And with that, I was able to present my research. I was able to see and meet, a Nobel Prize laureate. I was able to meet with people that are in my field of research, and get comments and criticisms and help with being able to progress my own work. But some of the things that I would say for you all is, ask questions and reach out to people. One of the best assets that you all have right now is the fact that you're a student. And if you have an email that ends, in .edu, which, a lot of college students, I'm not sure if high school students will have that, but regardless, you being a student, people are more apt to respond to you and to acknowledge some of the things that you're saying. So feel free to reach out. Don't ever feel shy, because we like students. We have students right now in the clinic. I'm a student still, but we still have undergraduates and other people that come in the clinic all the time that just want to get exposure. And then what you can do while you're in school is doing kind of what I did, and just find your way. Find what works best for you. Find the right environment and really absorb as much of those experiences as you can. I'll tell you, my basic level chemistry class, it still pops up. Everything from it still pops up. I'm writing my dissertation for my PhD. Everything I learned in high school grammar and English still pops up. I still have to go back and remind myself about equations from old math books. I have to, and some of you might not have enjoyed that your first time through, but I assure you it is fulfilling when you get the opportunity to use it for your own work. It's so much better than your teacher holding you down and making you do an exam for an hour with no calculator. But it's a learning curve that as you progress, you get the opportunity to find out why that stuff is so important. Is it a lot of work? To be fair, it all of it is going to be a lot of work. Nothing worth it ever comes easy. So at some point, I come into work every day, and I don't even like to call it work. I just call it because that's what everyone else thinks of it as. It's work. Well, it's not work to me. It's fun. It's fun. I get to go into the lab. I get to mix stuff. I get to make things bubble and blow up, and those are fun days in lab. I get to walk in with patients and get to meet with them and talk with them and help them through some of the problems that they're having, and it's just fulfilling. It's not hard. It's not hard to do that. It's much harder to me to not have that purpose, to not have something to do. And so that's something else that I would encourage you all to do, is find a purpose why you're doing this. It's easy to say that you want to go into this stuff because you want to help people, or you want to win a Nobel Prize yourself, and all those are good things. We all want to be able to do that, but being able to really nail down your purpose and why you're wanting to do all of this can not only helps you tell your story, but it also helps you just know yourself, and it makes things not seem hard because you're just fulfilling that purpose. Getting to serve people is an honor to me, so it's not work to me. It's a privilege to get to come in and get to do this for these people. It's a privilege to get to take my research and extend the knowledge base that we've on for many years, because anything that I do has been built previously by other people. I stand on the backs of the giants that came before me, and so you really get that opportunity to push that, and it's a privilege and an opportunity. Some of the other things that they ask is, about the environment and the students. Is it a friendly environment? Is it extremely competitive? It's both. It's both. Especially here at OSU, we are a family-oriented school. And by family, I mean that all the students, all the faculty, all the staff, we're all family. and we help each other. The competitiveness comes, it's you versus you. And while you have all these people next to you that'll help you, it's still always, we're always competing against ourselves to make ourselves better. And that's kind of the uniqueness here at this school. Unfortunately, some other schools will have, inter-family competitions that, are, that excludes people and puts people, alienates them. And that's just not the environment that we have here. It's what can they do, or what can we all do to make each other better? And that's, as soon as I get off this call, I'm going to go into a room with 7 other medical students, and we're all just going to be bouncing ideas off each other. We're always going to be trying to figure out what's the next best thing for, whether it's ourselves, taking care of ourselves, or whether it's for the patients and being able to help them, whether it's for the next exam that we have to do. And the same goes for in the lab. When I'm in the lab, I have research assistants that, or techs that will help me. It's not about competing with each other. It's about just trying to get this stuff done and get it done the best we can in the most accurate and reliable and valid way we can. And so, there's healthy competition is what I would refer to it as. And then you might ask yourself, well, 7 years, he's been in school for 7 years. What does he have a life? Does he do anything but school? And of course, during your master's, it's a master's program they're typically built around being able to do things like work. You don't have weekends that you have to go to class. You might be stuck, finishing a paper over the weekend. But there is an ability to balance your work and your life schedule. And say you go on and you want to do your PhD, well, they pay you for that. They give you the money to be able to focus on doing the research for the institution, which is also the research that most of the time, it's also the research that you're doing for your own degree. So there's definitely an ability to be able to balance everything, because life goes on. I didn't just have 7 years of being in school. Like I said, it's been a journey that has all interwoven itself into, this big, beautiful journey that I've been on. And so let's see what else. So as far as affordability, again, concentrating on your coursework, trying to do well as much as you can on grades. It's so that you can then apply for scholarships, grants, any of that stuff. I personally did not have a lot of that. Again, I didn't have a previous family member that was in medical school or in graduate school. I didn't have anyone that could kind of show me the ropes. So, unfortunately, I have a lot of debt that I put on, but also I know that at the end of this, that's something that I'm going to be able to pay back, and gladly will so, because this is an investment into you and your future. It's for you, yourself, it's for your family, and anybody that's going to be in the future with you. So, if it comes down to, money, I would go back to your purpose. Sometimes you take on that debt to be able to fulfill that purpose, and that's the same for any business. Sometimes businesses take out loans because they need to carry out their mission statement. So it's no different in that. It's just making sure that you have a purpose and that you're willing to do what it takes to be able to fulfill that purpose. And sometimes that means taking on money. But there's also plenty of avenues to be able to get scholarships and grants. Like I said, my PhD itself, the tuition is entirely covered by the school. And then they offer me money each month to work for them, whether that's teaching students or conducting my own research. And so again, I would just tell you all, find your purpose, find what interests you, try to find a good environment to be able to fulfill that purpose. And just always ask questions, always be curious, always reach out if you want, and try to get more experiences, because the more you find out what you like and what you don't like, the more you can figure out where to go next on your path. And it's almost never a straight line, especially for me. There's plenty of students that I'm around that have had the typical, they go to undergraduate, they're biology majors, they graduate, 4 years, and they go straight into medical school, or they go straight into graduate school. And that's not always necessary. I also know students that have been out for 10, 15, 20 years, and they come back and they become doctors. I know a research tech right now that's over 50 years old that is now going back to get her PhD. And that's good. I applaud them for doing that, because they are capable and competent, and we just need as many people out there that have that mission and have that purpose. The more the merrier. Just grows my family, my research family, my clinician family, my OSU family. And so we welcome you all to come and join us and further the mission. And so I think that covers most things. I don't know if there's any questions or anything.
Yes, if you have any questions, feel free to unmute and ask those, or again, if you want to chat those. But Dalton, can you kind of walk us through, I know as like high schoolers, it might be a little bit abstract as far as like the milestones, as far as like graduating from high school, graduating from college, what it looks like to become a graduate student.
Sorry, I was reading the chat. Can you briefly restate that?
Yeah, can you just kind of talk about milestones as far as like your high school diploma and then your bachelor's, kind of what the process looks like to get those degrees that you're working towards?
Sure. So I graduated high school and then went on to my undergraduate program. And as I mentioned, I went and played sports for the first 2 years. And then my second 2 years of my undergrad, I went to a new university, started that new program. So it was high school, and then you go on to your undergrad. And that might be different for some people. You might start off at a junior college, 2-year junior college, and then go on to a 4-year college, a university afterwards, or you might just enter a 4-year university. Either route is fine, but at the end of it, you do need to have a bachelor's degree before applying to any of these graduate programs. Does that kind of, does that answer that?
Yeah, and then I think you saw the chat, but Emily wanted to know what made you choose OSU over other schools.
Yeah, so I had visited both OU and OSU, and it was less to do with the entirety of the school at first and was directly related to the researchers, because I had originally planned on doing my PhD and doing research during my undergrad. So I was looking for who was doing the research that I wanted to learn from. And so there was a professor over at, I'll just say at a different university, that I had reached out to. Well, after a few months of speaking with that person, they had told me not to put all my eggs in one basket, which is always a good thing. But it'd come out that that person was being asked to leave the university because of doing some unethical and illegal research stuff at that place. And so that essentially demolished that route for me. And so I decided that I was going to follow one of his colleagues who came over to OSU and started up in their health and human performance program. And so while I was here, this was not affiliated with OSU CHS yet, but while I was there, not only did I get the opportunity to work with that new professor who was doing some of the research that I wanted to be involved with. But I also got my foot in the door at working at the hospital, the local hospital. So Stillwater is kind of, it is a bigger university town, but it's also small enough that you can get your foot in the door in a lot of places. It's got that smaller hometown feel. And so I was able to get more opportunities there. But then reaching out for graduate school, again, I reached out to OSU CHS, and just every interaction that I've had with them has been a positive interaction. The people here have been great to me. The stuff that they're doing over here has been great. And so I was already in the system. This is where I wanted to be, and it's the only place I applied to.
So I know,
Thank you, Emily.
I know it's a little bit different for medical school, but what does the admissions process look like for getting into graduate school for biomedical sciences?
So for the biomedical sciences, so this is why, I had to reach out years in advance, because I was in exercise science. And while that does cover a lot of health and just health related subjects, it didn't necessarily cover all of the sciences, the hard sciences that I needed. And so reaching out to your recruiters and the people at those universities to find out what is needed to be able to join those programs is good. So there might be, certain courses you have to take, just like it for medical school. They require you to take certain amount of biology courses, or certain amount of, physics or chemistry, or, some of those courses. But then also there are entrance exams. So many of you all will either have or will end up taking an ACT or an SAT to enter college. There's also tests to enter graduate school. And I believe that's the GRE, graduate something examination. And so it's I believe, if I recall right, it's been a while now, so it's probably changed, but it's about half math and half grammar and reading comprehension. And so you will take one of those exams, and not all places rely heavily and solely on that exam. So for any of your applications for any school, most places will look at the whole picture. So, your GPA might not be a 4.0, but we see that you've gotten all these volunteer hours. We see that you're heavily involved in research, and we see that you're doing this, and this. That's what's good about OSU, is that they look at all that stuff. They look at so many different things to see if you're a good fit for this family. And then I see another question. It says, what are some of your recommendations for high school, or for things high schoolers can do to determine if medicine might be the right fit for them? That is hard, because during COVID, a lot of things shut down. And so what I would say is try to get into clinic. We've had pre-med students with us today in the clinic, getting a feel for, is this the right place? Is this what they want to do? And that's the best way that I would say to find out. Also, you need to have a feel for your courses. How did the courses make you feel? They're not going to always be the easiest courses, but are they things that make you excited? Does learning biology make you happy? And it might not. Maybe physics is what makes you happy, but do these sciences, are they giving you that feel of, this is something I could do as I go forward? And ways to prepare for pre-med, again, you got to learn how to learn. Really nothing will happen if you don't attend your courses. Nothing will happen if you don't, you won't be able to progress if you don't take care of your coursework. It has to be done. It doesn't have to be a 4.0. You don't have to get 100 on your ACTs or your SATs or your GREs, but you do have to show up, and you do have to put the work in, and you have to do so well on those. But being attentive to your coursework will help you with all of this. And it's the same thing in medical school. What's something, and then thank you again, Emily. And then Savannah asks, what's something you wish someone would have told you before you got into medical school? Ooh, that's a hard one. That someone would have told me that. So I was speaking on the work-life balance. While it is possible, it is also very easy to lose that balance. And so you really have to work at making sure that you are being attentive to other things in your life. Because it's very easy to get wrapped up in the schoolwork. It's very easy to get wrapped up in, having an exam every other week. That sometimes you forget, hey, I need to go see that friend that I haven't, spoken to in, a couple weeks or a couple months. I haven't spoke to my mom in a week or two. I need to reach out and make sure that I'm being attentive to my other relationships. And also self-care. Did I get exercise today? Did I eat anything that wasn't fried today? Did I eat anything that wasn't, grab and go? Was I eating out of the vending machine for the past 3 days and didn't realize it? So, just being attentive to some of that stuff is what I wish I would have known. And I think I was told that. I just, sometimes when you're on a mission, you say, well, that's something I'll figure out as I go. And most people do.
So you mentioned that you've done a lot of research. What is your favorite area of research?
Yes. So the exercise science stuff that I did as an undergrad was really fun. Getting to work with those patients or work with the senior adults and watching them do their exercises improve. And so that was really fun. Now I do a lot of what they call bench lab research, where I'm sitting there doing a lot of molecular biology experiments and doing a lot of mixing this fluid with this fluid and then sticking it in a machine. And so that's that. And that's a lot of kidney research. But personally, I'm in cardio research. So I like anything that has to do with blood pressure, how the heart beats, how blood flows through the body. But right now, specifically, my dissertation is working on how our kidneys regulate water flowing in and out of the system and how that influences blood pressure. And so the beautiful thing about the research is that in graduate school is that there's this rigidity, or this they kind of walk you through, you got to take this course, you got to take this course, you got to take this course. But then they also give you the availability and the freedom to kind of venture down any kind of research that you're interested in. They welcome that. They want you guys to ask questions. They want you to be the next Nobel laureates, and in doing so, they give you that freedom. So hopefully that kind of answered it, and I kind of went off on a little spiel.
Okay, well, do we have any last minute questions? I'm sure you're pretty busy right now. What are you, is this your first rotation?
Yes, so this is my first rotation. This is osteopathic manipulative medicine. So no drugs, no bugs, just helping the patients with our hands. And so it's a wonderful experience getting to see the patients and getting to treat the patients, and then sending in the attending afterwards and the patient saying, I'm already feeling better. It's really fulfilling work on this rotation.
Okay, perfect. Well, it doesn't look like we have any more. If you all think of anything, feel free to email me and I will get that over to Dalton so we can get that for you. Okay, perfect. Well, thank you so much, Dalton. That was a lot of great information, super helpful as these students are considering biomedical sciences and what graduate school could mean for them. So thank you so much.
Yeah, thank you.
Okay, well, let's go ahead and kick off this session. So today we have Aubrey Brink with us from the Forensic Sciences program. She is one of our current students. And I'm going to hand it off to her in a second. But just to let you guys know, again, we are recording so that at the end of the week, we'll send out all of these sessions so you guys can watch them back, or if someone's not able to make it, they can watch those as well. Again, if you have any questions, feel free to shoot those over. At the end, we'll open the floor if you have any. So be thinking of those as we go. And for now, I will hand it over to Aubrey.
Thanks. So I am Aubrey, and I am in my second year of the Forensic Science Master's program here at OSU. I'm actually planning to graduate in December. I'm from Fayetteville, Arkansas, so it wasn't a far trip for me to get over here, but so I decided to go into the forensic sciences actually in my junior year of my undergrad. It all kind of happened because, so I knew I wanted to do chemistry, but I wasn't really sure where I wanted to go with that. And so I kind of just got online and was like, okay, like what are my options? And I kind of fell into forensic science, and I ended up doing an internship at the Arkansas State Crime Lab, where I studied arson and ignitable liquids and the longevity of like their identification on certain materials. And so that's when I was like, this is actually what I wanted to do. So from that point, I started looking at grad programs. I applied here and I applied to a couple others, and overall just this seemed to work the best financially for me. So this is where I ended up. And so currently I am in the forensic science program, but my focus is toxicology and chemistry. So I do a lot with illicit substances, specifically fentanyl, which is actually what I'm doing my thesis on currently. So that's exciting. There are several other degrees available in our program. There's DNA, there's arson, explosives, firearms, and tool marks. There is psychology, and there's one other one that investigative sciences. So like crime scene investigation. After I graduate in December, I'm hoping to find a job in a crime lab. Long term, I really want to do kind of arson and explosives, but I also really enjoy like toxicology and like how drugs function in the body and how that can affect people and like impair them. So I'm kind of open to possibilities. It's just wherever life takes me. Prior to coming here, I got my bachelor's degree in chemistry from Hendrix College in Conway, Arkansas. And I think one of the most important things to remember is like you don't have to have a degree in forensic sciences to get a master's degree in forensic sciences. Biology, chemistry, any of the natural sciences are a good option. It also kind of leaves you with more possibilities if you decide like, oh, like forensic sciences isn't actually what I wanted to do. For me, like I said, I didn't know coming out of high school that I even wanted to go to grad school, or really until the middle of my college experience. So it's not imperative for this field that you know right away what you want to do. Like there are a lot of options that I feel like that's really important to remember. This particular program is a 2-year program, but it's kind of been reformatted in the last year or so. And I am actually graduating in a year and a half, but I also surrender FEPAC accreditation with that. But I don't think it's going to affect me in the long run based on the experiences that I've had while I'm here. Because so currently I'm not only working on my thesis focused on fentanyl, but I also work as a clinical toxicologist in a local lab. So I test urine samples for drugs. And just the hands-on lab experience is a lot more valuable than like taking a bunch of classes, in my opinion, especially at this level. So that is definitely an advantage here. It's kind of odd, like where I came in during COVID, because I haven't really had any interactions with other students in either the toxicology like section or any of the other sections. It's kind of just been like me on campus. I had one other coworker, but she ended up leaving. And so it's been like really kind of odd because there isn't that like human interaction to a certain extent, and I think that that'll change as like we kind of reintegrate back into like a normalish world. Um, but and then so like I said, I also do work 2 jobs and have since I started the program. So it's definitely possible to like fund your education while doing it. And a lot of the professors, especially like my advising professor, actually hooked me up with the 2 jobs that I have. So he was like really adamant about me being here, being able to afford school. And I think that's like a huge like plus for kind of this program in general. Yes. I don't know what else.
A lot of students probably have seen, CSI or, crime shows. Do you think it's anything like those, or is it completely different?
I think to a certain extent, it's kind of like that, but you have to remember that like everything portrayed on TV is like a really like sped up process. Like things aren't like instant gratification like they make you think that they are. And so there are very complicated problems that have to be kind of like worked through. And I think that that gets brushed over. Yeah, like people don't really understand like, oh, like this actually takes time. Like we actually have to run tests and do analysis. It's not just, oh, the computer tells us the answer kind of thing.
Mm-hmm. So what does the admissions process look like to get into the Forensic Sciences graduate program?
It was not hard. I think it's a personal statement. It's 3 letters of recommendation. And I think that they've gone away from GRE scores. I can't say that for certain. I took the GRE before my admissions process, but I think that they might have gone away from that. That was not something that I prepared for, though. In undergrad, I had absolutely no idea. And all of a sudden, they were like, oh, you need to take the GRE. And it was things that I had not looked at in years. So if I could offer a piece of advice, if you need a GRE, you might want to kind of just look it over, just algebra, geometry, things that you don't really like focus on in your undergraduate, but somehow come back and become relevant all of a sudden.
When do you recommend they start preparing for that?
It's really, so I took mine my senior year of undergrad, so probably mid-junior year. It's not a huge pressing thing. It's just kind of something to like keep in mind. Same with like kind of the whole admissions process. It's just really important that you like keep in mind what the deadlines are. And I think ours are in early February, I think, but I'm not sure.
Okay. And what are like the big milestones as far as like, what's the process you have to go through to get a master's degree? Like that high school and then you go to college?
Yes. So high school, undergrad degree, and then so master's is kind of like interesting. And there's not a real specific structure to master's programs like there are with undergrad programs. Like usually in undergrad, your advisors are very like clear about, hey, this is where you need to be to like graduate, or like in my experience they were, and like these are all the classes. But the master's program here is a lot more flexible. It's kind of like you take what you need to take to get where you want to be. The big things for the master's program are the thesis requirements, which several of our degrees actually have a thesis option or a non-thesis option where you can do more of like a creative component. It's not as structured. Thesis is a lot more like by the guidelines, like it's very like specific. So it's kind of just what you want to get out of it and like where you're trying to end up, whether you want to be more research based moving forward or whether you want to kind of take it in a different direction. And then I think they also require kind of like a comprehensive exam towards the end of your time here, which is just kind of like a general knowledge, like what have we learned, what are you taking out of this kind of thing.
Okay. And you've mentioned a thesis and dissertation. Can you kind of tell us what those are?
So essentially the thesis is just original research. It's usually ends up being funded by somebody who needs research done, and they reach out and they're like, hey, can you do this for us? Which is why like mine's over the aerosolization of fentanyl. And so the CDC wanted to know. And so that's what I'm doing. But essentially the thesis is just original research that you conduct. It kind of varies in like depth, but there's just a very like specific template that you have to follow essentially to write up a research paper. There's an introduction, a lit review, so kind of like what's already out there, what are you basing your research off of, like how did you come to this idea in the first place, and then your original research, your results, and then like what you're going to do with it moving forward or how it can be applied on like a larger scale type thing.
Okay. And what has been your favorite thing about graduate school?
Probably just, so my undergraduate experience, I did get my degree in chemistry, which was super beneficial, but there was no like specialization. It was just general chemistry. And so I knew forensic science really interests me. So the master's program's really given me like a lot of room to kind of just like learn about the field in general, which I really enjoy because there are a lot of aspects that I don't know that I recognized as being forensic science. And like the thing is, like forensics can really be applied to like any field, which I don't think I realized going in, because the word forensic is really just used to talk about like something in conjunction with the law. And so there's just a lot more there than I ever would have expected. And so getting to learn about different stuff is just really probably the most interesting thing for me.
Yeah. What's been your favorite thing to study?
Probably pathology. Just because with like talks, you deal with like people like overdosing and like things like that. So to see kind of how that applies on like kind of a larger scale and like what role tox plays in like autopsies and like things like that was really interesting for me. Yeah.
And what's pathology?
Pathology is essentially just like determining the cause of death, cause, manner, and there's another one. I can't think of it right now.
Put you on the spot for it.
Sorry about that.
Oh, no, you're fine. What's been the most challenging thing about graduate school?
Probably the most challenging thing is the trying to balance work and life, because what people don't really understand, or like I didn't going into grad school, is that grad school is your life. And like you have other people in your life, like especially like your friends, they're like, oh, like come do this and like all these things, and you're just like, I can't, like I have to get all of this done and like I have to pay the bills. And so the work-life balance isn't always there, but it's also one of those like, this is a year and a half, 2 years of my life, and then I can move forward with my career and I'm going to be further along for it in the end. There's also one of the other harder things for me is me personally, I felt like there's been kind of like a lack of like communication first to a certain extent about like what expectations are, what needs done, and it's improved over time. And I think a lot of that was just like, I moved here in 4 days to try to start this program, like with no warning whatsoever because of COVID and everything. And so for me personally, that's been a struggle, but overall, I think that it runs rather smoothly, to be honest.
Well, what's been the toughest subject that you've had to study?
I have to think about what I've studied. Probably advanced toxicology, just because there's a lot of really biologically based things that happen inside the body to make drugs work the way they do. And as someone with very limited biochemistry or biology background, sometimes understanding that is a bit confusing. But I think it definitely challenged me in a good way to be like, oh, okay, this is all starting to make sense. Like drugs act on receptors and like they have this effect like overall in the body, as opposed to just like, oh, you take this and this happens. Like it's a long like chain of events that gets you to the final result.
Sorry, I think someone's got a leaf blower outside of my window here. What advice do you have for these current high schoolers that are considering or kind of deciding what they would want to do long term, if that would potentially be forensic sciences? What do you recommend?
I don't necessarily recommend like pushing yourself super hard at this point. There's a lot of time, and I feel like where some programs you might need to know going into undergrad so you can prepare for coursework and things, it's not quite as imperative with a program like this. Like I said, I had no forensic science background coming into this program, and I've had absolutely no problem trying to get through it. Yeah. As long as you focus on a natural science and you kind of like keep in mind like, hey, this might be something that I want to do, you're really going to be okay in the long run.
Okay, well, if there's any questions or anyone's been curious about anything, whether that be the admissions process or her experiences since she's been here, what she's studying, feel free to send those over or unmute and ask those. Now's really the time to kind of get those questions answered. Give you guys just a few more moments. Okay, well, it looks like you answered all the questions for now. Again, if you guys have any questions that you think of later on, feel free to send those over to me and I will pass those on to Aubrey so she can answer those for you. But as for now, thank you, Aubrey. That was awesome to hear all about that and your experiences and what it means to be a forensic sciences student.
Thank y'all for having me.
Yeah, of course. Okay, well, that is it for 411 for today. I'll put our schedule up on the screen and we'll pick back up first thing tomorrow. We have our physician assistant faculty question and answer. So it's going to be a similar format to this, kind of talking about what the program is, what schooling looks like. Then we'll have a parent and teacher session that later in that morning, and then we'll have a food allergy lesson from one of our recent graduates in the afternoon, and then we'll have a day off, and then we'll pick back up on Thursday. But it's been great having you guys today. I'll send out the Zoom information for tomorrow first thing in the morning, and other than that, I look forward to seeing you guys then. Have a great rest of your day.